week, last Friday was the last time we looked at this, where we could see how the K was represented. Now, the thing is, we ended up with two types of K. Kc was based off measurements in units of C standing for concentration, molarity, good. Kp was based off units measured in pressure, atmospheres, right? And the question is, if with these two Kps and Kcs, are they the same number? And the answer is definitely maybe. It depends. It depends on a lot. So there are times that Kc and Kp are the same number, and those times are when in a balanced chemical reaction, the number of moles of reactants and moles of products happens to be an equal number. So in this case here, A and B, that represents 1 mole each, 2 moles total. AB, 2 moles total, same number of moles. In this case, if you have a Kp and a Kc, they will be the same number. However, we can conclude from that if they're not the same number, Kp and Kc are different. Now, we're going to use a formula to show how to translate between Kp and Kc, remembering that concentration and pressure are functions of the ideal gas law. When we express PV equals nRT, what we can say then is that pressure equals molarity, if we think of molarity as moles over liters, times RT. Yes, pressure equals molarity times RT. And in that case, I can see that pressure and molarity are directly related when RT is kind of thought of as a constant. And so what we'll do is we'll use this formula, which your book goes into a lot of pain to prove to you. And we'll say that not pressure but Kp, not molarity but Kc, times RT, but not just RT, RT to the power of delta N, change in moles of gases. That makes them translatable. So in this case, for instance, I've got 1 mole of reactant and 2 moles of products. Clearly, different coefficients. Clearly, Kp and Kc are different. When I'm calculating delta, what's delta mean? In 3 words. Final minus initial and products. Every one of them, reactants and products. Every time we look at a reaction, it will have reactants and products. And in this case, we can imagine that K is a number that is a quotient of them in the order products on top and reactants on bottom. So where it's tempting to say products over reactants equals K, I really want you to think of this K as a fraction. It's really equal to K over 1. Think of this as a fraction the same way you would think of the expression as a fraction. And if this fraction, K over 1, is in the neighborhood of unity, in the neighborhood of 1, a little bit higher is fine, a little bit lower is fine, within that region is fine. What we kind of mean is that you have a significant amount of both reactants and products. They're almost the same number, within reason. If you have a value of K that is huge, what that means is big number over 1. Lots of products over a few products. Now we're not saying the reactant concentration is 1. We're just saying proportionally it would be a big number to 1. Okay? Likewise, if K is a very small number, treat that small number, and I'm talking things like 0.000000004, small numbers like that, treat that as the number over 1, still a fraction. Where now we can see the reactant is a significantly larger number than the product would be, so we favor reactants over products. That's a test question right there. I want you to understand that K's size right there tells us the degree to which we have products or reactants. Got it? All right. A few more things. K must always be positive. Otherwise, there would be things like negative molarity and negative pressure, and that just doesn't happen. We won't worry about units with K. K, for all practical purposes for us, will be a unitless expression. K, for reactions that have solids and liquids, we'll ignore the solids and liquids, because in order to measure K, you need a molarity or a pressure, and solids and liquids have neither molarity nor pressures. K changes radically with temperature. If you'll notice on question number 2 of your assignments, I gave you a temperature, and then I gave that temperature again in question 3, and again in question 4. And the reason I'm giving you the same temperature over and over again is that means when temperature is constant, K is constant. But the moment I change K, temperature by even a small amount, K is going to vary as well, just like it did in rate laws. However, in rate laws, when reactions only went forward, we assumed that increased temperature caused them to go faster. In equilibrium, since reactions go forward and backwards, we can't tell what effect temperature has yet, but we will soon. Finally, catalysts make reactions get to the product side faster, or in this case, catalysts make us get to equilibrium faster, but catalysts do not affect the K value. So the use of a K of a catalyst won't affect the value of the equilibrium constant. It just might mean you get the forward and the reverse reactions to get to equilibrium faster.